So yeah, this talk will be about arithmetization-friendly primes and a new perspective on how to see primes from a hardware perspective, actually. And this will be one part. The second part will be about efficient constraint evaluation, and we'll try to merge those two parts in a nice way. Yeah, let's start immediately. So yeah, as I said, two parts. I will first talk about the trend towards smaller primes in the ZK industry. This is very easy to see nowadays. And then about this new perspective of how we actually could choose a prime if we have in mind custom hardware, custom chips. And yeah, the second part, so this may all seem very hard to actually compile to custom hardware, but actually it turns out that if we have the right tools, the right software, it's not so hard to do, and Phil will talk about that later in the second part. So let's start. Of course, this slide is with a lot of caveats, and many people here may not agree with the years down, but yeah, let's just say that many years ago we mostly had those large primes in ZK, and we still have them for some of the use cases, especially for ECC and stuff where we actually need those large primes. But in the last years we've seen that we actually go to smaller primes. So we had the Goldilocks prime, which is 64 bits large. Then we have these nice 31-bit primes, Baby Bear and M31 and Koala Bear and so on. Koala Bear maybe not as much used as the other two still, but yeah. And very recently we even go to 1-bit fields and extensions of that in Binius. So we see this trend towards smaller and smaller fields in ZK, at least where it's possible. For some proof systems, of course, it's not really possible to do that. So why is this the case? Why are we seeing smaller primes? Oh, well, it's quite simple, but the reasons are a bit different on software and hardware. So on software, we try to use as few limbs as possible for the primes. And we only have those, like, for example, 32, 64-bit registers or word sizes. And if we have, of course, a large prime, we need many limbs, we need many instructions, and in some cases it scales really badly with the number of limbs, so it's not so good. So we try to use smaller primes, and we then have a more efficient AVX representation. We can maybe do some things in parallel. Things like embedding overhead is also very nice if you use smaller primes, at least for real use cases. That's on software. On hardware, the situation is a bit different because we can do prime field multiplications natively up to some extent and with some caveats, of course. And the same is true for tower field multiplications in Binius. So there are things we can do differently than software. Of course, we have this trade-off also on hardware. Do we prefer to have a smaller area, or do we have prefer to have better latency? So there's this trade-off. Do we use Karatsuba, or do we just put in a larger multiplier? But in general, there are fewer restrictions on hardware. So we can actually decide which primes to use and which prime to build the hardware for. So how do we choose a prime? This is, yeah, it's not so new, right? Let's just assume we arithmetize something, for example, a RISC 5. So there are some properties we need the prime to have. For example, we need it to support some fast entity. This could be a very normal FFT or entity, or something like a circle entity. So in general, we try to have it high to audacity, or these other properties if we talk about, for example, certain entities. We also want to have it a fast arithmetic operations and fast model reduction. Sometimes this refers to the number of coefficients in the power of 2 representation of the prime. It's not always the case, but sometimes. And as a bonus property, so to say, we can also think about the power map being very low for a certain, the degree of the power map being very low, because for recursive verifiers or recursive provers, we can then be more efficiently if we consider algebraic hashes like rescue, for example. And then as a bonus question, we can think about the embedding overhead or the arithmetization friendliness of a prime. And this is something the first part of the talk will actually focus on. So yeah, what does this mean actually? So very simple example. Of course, we want to have few limbs, like I said before, and we want to have an embedding overhead which is not too large. So as a very simple example, let's focus on int32 simulation, which we do many times in zkVMs. And we can decide, for example, well, we can choose 8-bit limbs, we can choose 16-bit limbs, we can even choose 32-bit limbs if we want to, but we'd run into many other problems then. But let's just focus on these two cases here. And let's, of course, we need more elements if we choose a smaller limb size. So how does the circuit look like? Let's just focus on int32 simulations. So let's say we use 8-bit limbs. We add two int32 numbers, or we simulate the addition with the prime fields. And of course, it means that we need, for example, in this case, we need 16 elements in the trace, or the commitment in total, if we use 8-bit limbs, and we use fewer elements, 8 in total, if we can use 16-bit limbs. The carry limbs, they get added, or the carry bits in multiplication. In multiplication, it's a bit different, but yeah, the increase of the number of elements we need is more or less very similar, the same. So what's the solution here? Well, it seems kind of obvious. Let's just try larger limbs then. Let's consider some 31-bit prime. Both of them are, all three of them are reasonably fast. Let's use one of them. For the addition, we have no problem. We have at most 17-bit products. Or results, intermediate results. We can still store this very fine in a 31-bit prime field. The problem is the multiplication, because if we simulate the entire stuff with 16-bit limbs, then we run into the problem that some of the cross products may actually be 32 bits large. So the probability of that is actually not so low. And there's an example here on the bottom of the slide, and actually then we have a problem because the 31-bit field is not really sufficient for the cross product, and we cannot really use this, which in some way forces us to use the 8-bit limbs, which needs more elements in the trace. But the solution to that is also very simple. We just move to larger primes, right? Actually not, because larger primes are not really efficient on CPUs. Why are not they efficient? Well, we would need to use a 32-bit prime, even a 33-bit prime actually, and which means that native multiplications are probably outside the word boundaries, on some architectures even outside the double word boundaries actually. Also lazy reduction gets harder. We cannot really do nice addition chains, or like small addition chains even, without intermediate reductions. And all in all, it's not so good. But luckily, that's not what this topic is about, because we actually consider custom hardware, right? So what if we just ignore the boundaries we have on a CPU and talk about custom hardware? And we immediately see that the situation is very different here, because if we consider a custom hardware chip where we build the hardware for the prime, then if we have some prime size in bits here, which is slightly larger of a power of 2, it's not really a problem, because we can build a custom circuit for the reduction, for the addition, for the multiplication, and so on. Now, of course, if you're careful, you may notice that this may actually be a problem, maybe not for the compute, but for the memory, because it would mean that you would need 33-bit memory lanes and so on. But actually, there are also solutions to that. This has been done in the past, where you actually slice up the memory. So for example, you do it in parallelize, use a 32-bit lane, and then in another 32-bit lane, you can store 32 bits of the 33-bit, the missing bit of the other 32 elements. And just as an information, not an expert here at all, but apparently some FPGAs can already use 33-bit primes, because they include some parity bit for each byte they store, so they actually support already these slightly larger lanes. So what does this mean? That on hardware, again with some caveats, there's in general a similar cost for the arithmetic for similarly sized primes. This depends a bit on the structure of the prime and so on, but with some caveats, this is true. That's on the implementation side. What about on the proof side? Well, fewer limbs means fewer entities, makes the commitment faster in general, means the trace is more lightweight, and we also have an easier arithmetization, which may be easier for audits, for example. And this brings me to this term of arithmetization-friendly primes. So that's a concrete proposal. I found it pretty quickly with a Sage script, I think after 10 minutes or something, just setting the properties below. So that's a 33-bit prime. Why is it called Panda Bear? Because, I don't know, every prime is called something with a bear, and I think Panda Bear is not yet taken, so why not? It has a sufficiently high two-adacity. I think it's 24 or something, if I'm not mistaken, which is lower than some others, but still. It also fulfills this nice condition, the GCD condition, so you can use rescue, for example, with degree 3 power map. And it even has a low Hamming weight for fast reduction, if you want to do something like that. Actually, there are better primes than this one. I found them a couple of days ago. But so this is just an example of a reasonably efficient and doable 33-bit prime. All right, so what's the advantage in practice, right? So what happens if you actually do that? Well, so what's the setup? The setup is we have 2 to the 18 rows. We have in each row 16 integer 32 multiplications, so we try to simulate those. And it's very important to note here that these are benchmarks, the CPU benchmarks from Plonky 3. So just as a comparison, if we use 16-bit limbs, we need 144 columns, and we need approximately double the number of columns if we move to half the size limbs. And we see that if we use Baby Bear, where we can only use 8-bit limbs reasonably, we are a bit slower than when we use Panda Bear. But you may think now, well, that's like, what's the difference? Like not even 2 seconds for the commit and less than 1 second for the proof. So where's the advantage, right? We changed everything for nothing, essentially. Well, the problem is this one here, you see. So first, this is not a really CPU-friendly prime. It's really bad. You need to move to U128 for the product, actually. You cannot use U64. And we also know that the modular operator, the built-in operator, is notoriously slow. So we would need some nicer thing for that, some nicer reduction. And we're currently also working on that to do that. So maybe the fairer comparison is to take this new prime and to use it with 8-bit limbs. Of course, we can always go to a lower limb size. And here we see that the increased number of columns pretty precisely matches to the increased commitment cost and also has a big impact on the increased proving time. And of course, this is not like, especially in the proving time, this is not always the same for all the circuits. It very much depends on the circuits. But for the commitment, you can estimate it pretty easily. So we have done all these changes now. Let's assume we have some trace table where we decided to change the prime, to change the entire constraint system, and all of that we want to do on hardware, right? Which is intuitively pretty hard because we need to change a lot of things, and we already have this chip. So how do we do this? And it turns out it's actually not so hard to do if you have the right tools and the right software to do that. And yeah, Phil will talk about that now.
Thanks, Markus. Yeah, my name's Phil Hodges. I'm a cryptography engineer at Fabric, and so I work on the software side. Basically, what we've got at Fabric is a VPU, is what we call it, Fabric's VPU, that provides a whole bunch of custom instructions that help us do general, flexible, performant cryptography. And our job in the software space is to kind of bridge that gap between an entire start prover or zkVM and these individual instructions. And so there's some work to be done there. And what I kind of want to go over is sort of a case study on how we've tackled the sort of constraint evaluation in a start table. As Markus mentioned, there's all sorts of changes that somebody might decide to make, and that's the tenuous connection between the two halves of our talk, that Markus comes in and says, hey, we could rearrange all these constraints. And what would we do about that on the software side? So I've highlighted some different components of maybe a start proof system. These are the ones that I'm, they're not in every single proof system, but they're in a lot of them. These things in green are a bit more fixed as sort of components. Merkle trees, NTTs, they don't change quite as much. When somebody comes in with changes to these, they're not so fundamental, they're not that dynamic. And our approach to those has actually been to write essentially assembly level modules that perform these computations, and just they're blazing fast and they take all the advantage of the hardware that we can. But these things in orange, like the start tables, essentially, they're very dynamic components. I've been working a lot with SP1, and the SP1 zkVM enables power users to write their own, to change them all the time, probably find little efficiencies like Markus is talking about, and rearrange the start table entirely. And so we need a better approach than just handwriting all of these things, because there's like 40 of those in SP1 already. So yeah, that's what I want to talk about a bit here. And I decided that I'd use Markus's situation of this new 16-bit lim size with a new prime and his implementation of the multiplication as a good example to drive this. So this is Markus's implementation on the right-hand side using Plonky 3's Air Builder. So just going over some of the characteristics here, some of the details. We've got a row that's being taken from a Stark table. We are loading a whole bunch of data from that low, these A lows and A highs. We are computing a bunch of arithmetic on those, which essentially computes the multiplication with the carries and the limbs. And we're constraining them using, like, that's the Plonky 3 stuff, that builder dot assert 0. It's like this constraint needs to be satisfied. So this, I love Plonky 3's error builder. I think it's super flexible. It's awesome. What this implementation lets you do is it lets you instantiate that builder with something that works as the Stark prover. So when you instantiate it that way, what it does is it takes your Stark table, which has got your trace of your multiplication table or whatever other Stark table, and it loads in all those values from the trace table for each row, and then it does this arithmetic calculation, and it combines them, when you say assert 0, combines them with challenges that then compute the quotient polynomial, which is like the next step on in the proof. So that's great. The other thing that it lets you do, though, which was critical for my component, because there's, again, 40 of these different implementations of various things of various complexity, and I don't want to go in and re-implement any of this if I'm running this on our hardware. So what it allows you to do as well is instantiate that builder with something called a symbolic error builder. And so when you do that, then instead of an evaluation that says, like, here's the actual computation, you get a symbolic expression, which instead of having inputs that are actual integers that we're doing arithmetic with, it has symbolic variables which sort of reference a place in a trace table. So just going over what this actually is talking about here, we've got one variable at the top, which is an entry from a main trace table at index 0. We've got a second variable, which is an entry from the same trace table at index 2. We've got a third variable that's at index 4, and we're multiplying the first two and subtracting the second one, or the third one. And that corresponds exactly to here, when op is 0. At index 0, we've got A low. At index 2, we've got B low. And at index 4, we've got C low, and our first constraint there is A low times B low minus C low. So it actually takes this and automatically builds this, recursively defined symbolic expression. And this is super critical for making something that handles this in a dynamic way. So the first step for me when I was tackling this was convert this into a portable definition. And that's what this definition looks like. I'm not going to go over too much of the detail here because it mostly represents the same thing from above, from the previous slide, but it is just a bit more flexible. Full credit to this format to Bobbin, who I believe is at Meiden now, because he kind of gave us 99% of this, and that's essentially what we're using. But basically, there's some metadata that says what field that you're using, and there's some details of like variables that you can input into this, and the characteristics of the traces that you're going to use. But what it specifies is essentially is that same representation, is like, how do I calculate the constraints for this Stark table? And it does so using this list of nodes. And then there's a list of expressions that reference the nodes that says, like, this is the node that I'm interested in the output for. The nodes have like constant type or trace type, which is an input from a trace table, or operation types like multiplication on the bottom over there. And again, we've got a trace input at column offset 0 and a trace input at column offset 2, and we're multiplying those two things together. Same as before, that's A low times B low. So we convert into this. It's a JSON file, it's nice and portable, and instead of looking too closely at this and trying to make sure everybody's on board with that, I have a nice visual representation of it, which you can't read the details of, but you don't need to, because it's pretty big. And the reason it's so big is because there's actually, in his implementation, there's 8 multiplication operations per row of the trace table, and the same 3 constraints are applied to each of those 8. And so you end up with 24 little blocks here of the same 3 constraints 8 times. And the reason that there's not 24 outputs is because this actually includes the next step of folding in the challenge values. So the colors on here, the green inputs, the green boxes are trace inputs. They're inputs from a trace table. The yellow boxes, which you can hardly see, are they're challenge values, powers of a challenge alpha that get folded into the constraint evaluations. And then the blue boxes are the actual operations, like multiplication and addition. And then the output right there at the top is the single value. So if I've gone too fast, the summary here is that this is a specification of his start table and the constraints that need to be evaluated on it to get the quotient polynomial. And it's a big pile of arithmetic on a bunch of input values that needs to be evaluated on every row of the start table, say some 2 to the 20 rows. And so that's really nice. It's a specification of a program that tells you exactly what to do, and it's like broken down into essentially inputs and multiplication and addition. And that's the kind of portable definition that we need to make it easy to build a compiler. And that is basically what we did. I'll mention that as I was working on this, I keep seeing related things popping up. I think I read a blog post from Inganyama a couple months ago that basically described this similar process. Is like Plonky 3's error builder lets you get these symbolic representations, and then you can use that as a front end for whatever kind of back-end proving system you want. And this is great for us. In order to go from an implementation in Rust to something that we can pile onto our VPU, this is exactly what we need. Yeah. So what does that look like? I said we built a compiler. We did. There's a lot of details that go into that, and I'm not the one who wrote the compiler, but what a compiler looks like for this kind of special problem when our target is our custom hardware, our VPU, that depends on the architecture of the VPU. So that's what I'm going to describe just at the highest possible level. This is an actual diagram of some type of our chip, and one of the main characteristics of it is that there are 40 individual VPU tiles. And each one of these tiles is basically identical, and they are capable of doing a lot of arithmetic, and it has access to those performant cryptography instructions. Some of which, for example, the most simple example is that there are like 24 wide vector modular arithmetic instructions. So those can just absolutely rip through simple modular arithmetic. And so that's essentially what the compiler needs to do. Like that entire pile of arithmetic that I was describing, every single row of the start table is fully independent in its computations, essentially. So this compiler says, well, I know what the arithmetic that needs to be done is. I need to compile this into a program, and I need to split it up in 40 batches to send one batch to each tile, and I need to have each tile go through 24 at a time, load these into vectors, and just rip through that whole calculation. And of course, when somebody comes along and says, well, how about you just use a different number of limbs, completely change the constraints? Well, I can then just send things through the same pipeline that I've just described, and I don't even need to know what the constraints look like, because we can just generate this portable definition and compile it to a performant VPU module. Yeah, one other thing to mention is that we've done this specifically from Plonky 3's error builder, but really the easiest part of that whole process is converting Plonky 3's symbolic representation to a generic one that we use as an input. So as long as there is a symbolic representation of a constraint system for a start table in any system, we can use our same pipeline to do the exact same thing. Okay, so overview of the whole talk for two disjointed parts is basically that we want to encourage people to not just think about what hardware they can use for their cryptography, but also how you can design your cryptography with specific hardware in mind at the sort of protocol design stage, and more specifically that we might have chosen between different primes based on arithmetization friendliness or hardware friendliness and sacrificed one or the other, but that we might not actually have to, depending on what hardware you consider. And also that custom hardware can provide very straightforward and flexible acceleration of Starks in different provers, as long as you have the right tools. And that's what we're doing in the software space at Fabric, is we're trying to build those right tools that apply to many different provers. Thanks, everybody.
Great talk. Was this investigation primarily driven by int32, like multiplication, and did you guys like profile other instructions as well?
Yes, it was primarily driven by int32 stuff, and primarily what the zkVM is, or some zkVM is doing. We didn't profile other stuff, so it's very true that for some circuits which do not really exploit int32 as much, it's useless to do.
Yeah, so my basically question is, you have entity as an example, which does butterfly, does multiplications, but none of this kind of translates one-on-one when it comes to hashers, like Poseidon hash, or I don't know, whatever hash you want to do. You're not really having as many multiplications. You are doing XORs and different things. So like, what's your feeling how this whole thing works in favor of hashing?
I think if you do plain hashing for, like if you rescue Poseidon, you don't have any, because you don't do int, you do, like, you're already native in the prime field, you don't need these tricks, right? If you use the hashing for the commitment, and this can be like shark, hedgehog, doesn't have to be Poseidon, you have the very small advantage that in the row-wise committing, or after the entity, after the inverse entity actually, forward entity, you are slightly faster. But that's, I think, dominated anyway by the number of rows, so it's not a huge difference there.
I was curious about kind of the same question, like basically what proportion of maybe more realistic examples actually includes like how much arithmetic. I think I looked in SP1, one of the larger examples they have built in, just ran it, and I was like, which start tables are actually filling up, which ones are larger? And arithmetic and multiplication in general were a larger portion than I expected. I don't remember exactly. It's a very informal sort of look, but that convinced me enough to be like, okay, I think this would provide some significant benefit.